the Nancy Grace Roman Space Telescope represents a groundbreaking leap in NASA's journey to unlock the secrets of the cosmos. Named in honor of NASA's first chief of astronomy, the Roman telescope is set to launch around May 2027 and will expand our understanding of the universe in profound ways. This next-generation telescope, with a field of view 100 times larger than that of the Hubble, will enable us to observe distant galaxies, investigate the nature of dark energy, and, crucially, search for planets orbiting stars beyond our own solar system. Imagine a telescope capable of detecting planets that are millions of times fainter than their stars. That's exactly what the Roman Space Telescope will do with the help of its innovative coronagraph instrument, a specialized device that blocks starlight to reveal the faint glow of orbiting planets. Unlike traditional telescopes, which have only been able to identify exoplanets indirectly by observing the way they affect their stars, the Roman Coronagraph is equipped to directly capture images of these distant worlds. This will allow astronomers to study planets that we could previously only speculate about and will open up new possibilities in the search for habitable planets and perhaps even life. Over the course of this series, we'll dive deeper into how the Roman telescope is setting the stage for future missions that will push the boundaries of space exploration and planetary science even further. But for now, let's begin this journey into what could be one of the most transformative tools for understanding our place in the universe. If you're ready to explore these mysteries with us, don't forget to like, subscribe, and support our mission to bring you closer to the wonders of the cosmos. The Roman Coronagraph instrument is one of the most ambitious technologies ever developed for a space telescope, representing a giant leap forward in our ability to directly observe distant worlds. Unlike conventional telescopes that rely on indirect methods to find exoplanets, like observing slight dimming of a star's light when a planet crosses in front of it, this coronagraph will allow us to image these planets directly. Blocking out the light of stars has always been a challenge, as it's similar to trying to spot a single firefly next to a floodlight from miles away. Yet, the Roman Coronagraph is designed specifically to overcome this, detecting objects that are up to 100 million times fainter than the star they orbit. This represents a sensitivity up to 1,000 times greater than current space-based coronagraphs, opening up a new era in exoplanet discovery. Engineered with a precision that is almost unfathomable, the Roman Coronagraph combines a series of masks, prisms, detectors, and self-adjusting mirrors. These components work together in unison to cancel out starlight in multiple ways, creating a dark zone that unveils the presence of orbiting planets and other faint objects. Think of it as putting on a pair of noise-canceling headphones in the visual sense, only here, the coronagraph doesn't just block light, it fine-tunes the surrounding space to suppress it completely. By creating this visual silence around a star, we can reveal the dim glow of planets that, until now, have been all but invisible. This technology demonstration aboard the Roman telescope is a significant step toward more advanced future missions, such as the proposed Habitable Worlds Observatory. In the future, this next-generation observatory aims to search for Earth-like planets, specifically seeking conditions that might support life. But to make that leap, we first need the Roman Coronagraph to show that direct imaging of distant planets is feasible in the challenging conditions of space. Engineers and scientists are relying on the data and lessons from this mission to improve the technology further and adapt it for the dedicated search for habitable planets. The Roman telescope's coronagraph will not only capture visual details but also provide valuable information on the atmospheric composition of these planets. This opens the door to exploring planetary atmospheres for signs of gases like oxygen or methane, which could hint at the possibility of life. For now, the Roman Coronagraph's role as a technology demonstrator will allow it to break new ground, showing us how much we've yet to discover in the hidden, shadowed realms around distant stars. This is more than just a look at other worlds, it's the foundation of a new way of seeing the universe. In the upcoming parts, we'll look deeper at how this technology was built, tested, and integrated, showcasing the challenges and triumphs of preparing such an advanced instrument for its mission in the vast, uncharted regions of space. The integration of the Roman Coronagraph into the Nancy Grace Roman Space Telescope was a complex and painstaking process, requiring an incredible degree of precision and teamwork. Installed within NASA's Jet Propulsion Laboratory's clean room, this sophisticated device was carefully connected to the instrument carrier, a structural backbone that holds the telescope's core instruments in place. This skeleton of the observatory will house both the coronagraph and the wide-field instrument, allowing them to work in tandem to explore the cosmos. Each component of the coronagraph, from its delicate masks to its finely tuned mirrors and sensors, had to be meticulously aligned to ensure it would function flawlessly once in space. This phase of the mission is one of the most challenging, as even the smallest error in alignment or integration could impact the coronagraph's ability to block starlight with the required accuracy. Engineers have worked tirelessly to ensure that every piece fits perfectly, testing and retesting each component. Precision in the build is essential, down to fractions of millimeters. The mirrors, for instance, must adjust themselves in real time to maintain a darkened area around a star, even as the telescope moves. This kind of self-flexing capability, while remarkable, has demanded years of development, with specialists designing materials that can withstand the pressures of both space travel and the fine-tuning required for planetary imaging. Brandon Krager, lead mechanical engineer for the Roman Coronagraph, has compared the instrument carrier to a framework that supports each delicate instrument, ensuring they remain secure and aligned throughout the journey. Following the successful attachment of the coronagraph, the engineering team will perform a series of intense checks and calibrations to confirm its readiness. Only then can the wide-field instrument, the Roman's primary scientific camera, be installed, completing the instrument suite that will be carried by the telescope into orbit. As engineers bring this extraordinary device to life, they're not just building a telescope, they're creating a tool capable of answering some of the universe's greatest mysteries. The effort represents a union of human ingenuity and relentless pursuit of precision, all aimed at allowing us to peer more deeply into the cosmos than ever before. In the next part, we'll explore how this mission will break free from traditional observational methods, reaching for planets that may have remained hidden from us until now. Traditional methods of discovering exoplanets, like the transit technique, have revolutionized our understanding of planets outside our solar system. By observing small dips in a star's brightness as a planet crosses in front of it, astronomers can infer the presence of a planet and gather vital information about its size, orbit, and even atmospheric composition. However, this method has its limitations. It requires the planetary orbit to align perfectly with our viewpoint, and even when it does, the observable transit period is only a small fraction of the planet's total orbit. This restricts the data we can collect and leaves many planets undetected. The Roman Space Telescope's coronagraph instrument is designed to overcome these limitations, making it possible to image planets directly. Unlike the transit method, direct imaging allows scientists to observe planets continuously without needing the precise alignment of their orbit. This approach opens new doors in exoplanet exploration, especially for planets that don't cross their star's face from our perspective, planets that have remained hidden, simply out of our line of sight. Direct imaging will also give us insights into smaller and potentially more temperate planets, worlds that are harder to detect but may lie within the habitable zones of their stars, where conditions could be right for life. Another limitation of current technology is that most direct imaging has been limited to young, giant planets. These massive, hot planets emit a lot of light due to their relatively recent formation, making them easier to detect. The Roman Coronagraph, however, is a game-changer. With its ability to capture images of planets 100 million times dimmer than their host stars, it will allow us to observe older, cooler planets as well, potentially smaller and more Earth-like in nature. This sensitivity could reveal an entire population of planets that we've never seen before. The data gathered through direct imaging isn't limited to just the visual aspects of these distant worlds, it also provides a unique opportunity to study planetary atmospheres. The light captured from these planets can be analyzed to identify specific atmospheric gases, including potential biosignatures like oxygen and methane. For the first time, we'll have a clearer view of the chemical makeup of these distant worlds, offering tantalizing clues about whether they might harbor life. This leap in our observational ability brings us closer to understanding the diversity of planetary systems across the galaxy. Through the Roman telescope's coronagraph, we're not just finding new planets, we're discovering entirely new realms of possibility. In the final part, we'll discuss how this mission will pave the way for future explorations and how the Roman telescope's pioneering work will shape the next generation of space telescopes, designed to answer the age-old question of whether we're alone in the universe. The Roman Space Telescope's mission is more than a technical achievement, it's a step toward answering some of humanity's deepest questions. By pushing the limits of direct imaging, Roman will bring us closer to understanding the makeup of distant worlds and the forces that shape the cosmos. As it captures images of exoplanets we've never seen, the telescope will not only broaden our scientific understanding but also lay the foundation for future observatories focused entirely on finding habitable planets. This mission is just the beginning. Insights from the Roman Coronagraph will drive the development of even more advanced telescopes, like the proposed Habitable Worlds Observatory, which aims to directly seek Earth-like planets that could host life. The Romans' data will refine the methods and tools used to identify these worlds, making the search for life beyond Earth more focused and attainable than ever before. Imagine a future where we not only discover distant planets but understand their atmospheres, climates, and perhaps even detect signs of biological activity. The Nancy Grace Roman Space Telescope will prepare us for that possibility, teaching us to see through the glare of stars to uncover the hidden details of exoplanetary systems. It's a leap toward a universe where the unknown becomes known, where the distant feels within reach. If you're as captivated by the quest to discover new worlds and search for signs of life as we are, join us on this journey. Subscribe to stay updated on the latest developments in space exploration and witness each new step that brings us closer to answering one of the greatest questions: are we alone? Together, let's explore the cosmos, one discovery at a time.